Welcome to The Explainer. Today, we're diving into a real investigative journey. We're looking at the physics of sound, and more specifically, the precise methodologies used to measure occupational noise. We'll break down exactly how professionals get out there in the field to track, quantify, and ultimately manage the noise that workers are exposed to every single day. Let's get into it.
Think about this for a second. How do we actually quantify a threat that is completely invisible and constantly fluctuating? I mean, you can't see noise. You can't just catch it in a jar. Yet, if it goes unchecked, it literally causes irreversible hearing loss by damaging those sensitive little cells deep inside the ear. So, because we can't see it, we have to rely on a very specific set of tools and math to bring this invisible hazard to light.
And that brings us to the core mantra of occupational noise management. It's simple. Identify the hazard, assess the risk, and control the exposure. This is the absolute foundation of our entire investigation today. We can't control what we don't understand, and we definitely can't understand what we haven't properly assessed. Now, every jurisdiction around the globe might have slightly different laws, but they all share this exact same sequential goal to stop hearing loss in its tracks.
Okay, so here's our roadmap for the explainer. We'll start with the invisible workplace hazard, then look at essential noise measurement tools, move into decoding acoustic parameters, check out the types of assessment surveys, and wrap up with calculating worker noise exposure.
All right, part 1, the invisible workplace hazard and understanding the threat.
I actually love this quote from our source material because it just perfectly hits the nail on the head. Rarely is workplace noise static or steady, and even if it was, a moving person would receive a variable exposure. Think about your typical factory floor, right? Machines are cycling on and off, production speeds up, slows down, and the workers themselves are walking around, moving closer to and further away from different sound sources. Because of all this constant movement, just observing the room isn't enough to assess the true risk. We really need objective data.
Moving on to Section 2, Essential Noise Measurement Tools. These are our weapons of the trade.
So, this first image brilliantly illustrates an absolutely crucial tool, the acoustical calibrator. Look, before you even think about measuring workplace noise, you have to be 100% sure your equipment is accurate. This little device fits right over the microphone of our measuring tools and produces a fixed, precise sound pressure level, typically at exactly 1,000 Hertz. We do this field check before and after every single survey. If the meter is off by even a tiny margin, boom, we know our data isn't reliable. It's basically the ultimate reality check for our gear.
Once we're calibrated, we bring out the real workhorse of acoustic measurement, the sound level meter, or SLM. Let's look at the components. It all starts with the microphone, which acts as a transducer, and that's just a fancy way of saying it detects physical sound pressure waves in the air and converts them into a measurable electrical signal. That signal then gets boosted by a preamplifier, refined by a range control, and passed through a frequency filter. Usually we use what's called an A-weighting filter because it mimics how the human ear actually hears different frequencies. Finally, it spits out a nice, readable number on a digital display in decibels, or dBA.
Now check out how we adapt that same technology for a moving worker. This block diagram of a personal noise dosimeter shows the same basic microphone and filters as the sound level meter, but it functions as a wearable device. See the clock and calculator icons there? Because a worker is moving through varying noise levels all day long, the dosimeter uses its internal clock and calculator to continuously sample the sound. It essentially computes the worker's accumulated noise exposure over their entire shift. It does all the heavy mathematical lifting for us while the worker just goes about their day.
All right, Section 3, decoding acoustic parameters or making sense of all this data. Now, the absolute key to noise measurement is understanding the exchange rate. In most international standards, we use a 3 decibel exchange rate, which is also known as the equal energy rule. So here's what that means in plain English. Every single time noise increases by just 3 decibels, the physical sound energy essentially doubles. Crazy, right? This means workers can accumulate the exact same, potentially damaging noise dose by being in slightly lower noise for a long time or slightly higher noise for a much shorter time. If a machine gets just 3 decibels louder, a worker's safe exposure time is literally cut in half.
Because noise is always fluctuating, we desperately need a way to average that energy over time. You are going to see this symbol everywhere in noise assessment. Let's break down the acronym, LAEQT. The capital L stands for level. The A tells us we're using that A-weighting filter that mimics the human ear. The EQ stands for equivalent continuous, meaning this is the average sound level using that equal energy rule we just talked about. And finally, the T is the specific time period we measured, like an hour or a full work shift. Basically, it takes a chaotic, spiky graph of sound and smooths it into one clean, equivalent average number. A real game changer.
Which brings us to Section 4, Types of Assessment Surveys. Let's take this investigation out into the field.
A professional noise investigation isn't just wandering around with a microphone. It follows a very strict three-step progression. We always start broad with a basic preliminary survey, just to see if a problem even exists. If it does, we move to Step 2, a detailed sound level survey to map out the environment. And finally, Step 3 is a specific noise exposure survey using dosimetry to measure exactly what individual workers are experiencing. Let's see how these actually work in practice.
So the preliminary survey is our initial screening step. And here is a fascinating, incredibly practical rule of thumb for you. You don't always need a fancy meter to know you have a problem. If you are standing one arm's length away from a colleague, and you have to raise your voice just to be understood above the background noise, well, the sound level is likely greater than 80 dBA. That is the threshold. If you have to raise your voice, that immediately triggers the need for a comprehensive, detailed assessment.
Once that detailed assessment is triggered, we have two main ways to conduct the investigation. Over on the left, we have the Area Sound Level Survey. Here, the investigator walks a predetermined grid right around the factory floor with a handheld meter, mapping out the machinery noise. This is huge because it helps us find the loudest machines, so we know exactly where to prioritize physical engineering controls. Then, on the right, we have personal noise dosimetry. This approach completely ignores the room and instead shadows a specific worker, measuring exactly what their ear receives throughout their unique routine, giving us their true personal accumulated dose.
Okay, let's wrap this up with Section 5, calculating worker noise exposure and actually protecting the worker. Take a look at this spreadsheet here. It perfectly captures a day in the life of a woodshop carpenter. By using the data we gathered with our sound level meters, we can list out every single job activity they do. Hammering, using the bandsaw, the planer, the router, the whole shebang. We log the sound level for each tool and the estimated exposure time in minutes. Then, the spreadsheet calculates how the partial noise doses from all these different activities combine into a single daily exposure level.
Now, really look closely at the math here, because this is where that 3 decibel equal energy rule really shows its teeth. Our carpenter spends 30 minutes hammering at 89 dBA. That contributes about 15.75% to their daily allowable noise dose. Just a minor fraction, right? But look at the router. It operates at 96 dBA, which is significantly higher energy, and the carpenter uses it for 2 hours. That single tool delivers over 317% of their allowable daily dose. This massively overexposes the carpenter, and without this specific breakdown, we honestly wouldn't know exactly which tool was the main culprit.
Now, in a huge factory, we obviously can't slap a dosimeter on all 500 workers every single day. That's where statistical sampling comes in. We identify groups with similar exposures, say all the forklift drivers. We sample at least 3 individuals, or 20% of that group, and here is the absolutely crucial safety mechanism. We take the highest measured noise exposure from that sample and assign it to the entire group. We assume the worst-case scenario for everyone to ensure maximum comprehensive protection across the board. Better safe than sorry for sure.
And keep in mind, all of these complex calculations, all the percentages and international criteria, they're all normalized against a standard baseline, an 8-hour nominal workday. That LAEQ 8-hour value we talked about, that's the universal measuring stick we use to determine if an environment is safe or hazardous.
But that leaves us with a final real-world puzzle to ponder today. If the entire safety baseline is calculated on an 8-hour shift, what happens to a worker's allowable noise dose when they pull a 10, 12, or even a 14-hour shift? Their ears have way less time to recover before the next day begins. How do you think exposure rules in our mathematics must adapt to protect workers when the standard workday just goes out the window? It's a really complex challenge that noise professionals have to tackle every single day. Thanks for joining me on this explainer, and keep asking the right questions.